We'll then just kind of jump in and introduce Cogan briefly. He's an assistant professor at Wright State University in Ohio. We will not touch off any conflicts around who owns the Wright brothers between North Carolina and Ohio, but we've got a little bit of both. And Cogan's going to talk about the KnowWhereGraph, nowhere with a K. And I think it sounds like it's going to be a nice mix of kind of foundational work and transition to actually useful stuff, creating what may be the world's largest knowledge graph today, which I'll certainly be interested to hear more about. So without further ado, I'll hand it off to Cogan.
All right, excuse me, great. My screen is sharing just fine and everything, and there's no Zoom artifacts.
You're good.
Okay, great. All right, well, thank you for the invitation and for the introduction. I'm going to talk to you about knowledge graphs, open knowledge networks, and then I didn't put it on the title because it was just getting to be a bit too much text, but I'll also talk about KnowWhereGraph. So a little bit about me. Here's my neat little picture of myself that my friend took via a neat art project, and it's very dramatic and I love using it. But aside from that, I'm currently a postdoc at Kansas State University, but in August I'll be transitioning to Wright State University, so I'm kind of like in this weird in-between state. But yes, that's just quick about me. So why am I in particular talking to you guys today? I'd like to think it's because I know a little bit about deploying knowledge graphs and like large publicly available that I kind of went through the growing pains of scaling up to something large that many people are going to use. And so, as John mentioned, I'm part of the KnowWhereGraph project, which is probably the largest open source knowledge graph in the world. I'll get into that a little bit later, but there's some other quite large ones, but it's arguable about whether or not they count as knowledge graphs. And then that's run on a traditional triple store, which is GraphDB. And then in contrast to that, I've worked on the enslaved ontology, which is part of the Enslaved Hub, which is funded by the Enslaved Peoples of the Historic Slave Trade Project by the Andrew W. Mellon Foundation. And this one was interesting because it uses a completely different architecture, and it's built on Wikibase, but it's slightly different or notably smaller in size. And then the last thing is, and as Catherine mentioned a little bit ago, I'm very interested in cyber training, especially for cyber infrastructure. And this has evolved into being involved with the NSF through their innovation sprint, where I'm helping develop the guidelines and criteria for what constitute the education gateway. So educating people and stakeholders and developers and other academics about what knowledge graphs are and how they relate to open knowledge networks and why they're important and the future in many ways for doing transdisciplinary research. So without further ado, I'll get into the actual content of today's talk. So very briefly, what we're going to go over are knowledge graphs and OKNs. I just want to make sure that we're using the same definitions or the same concepts for what it means to talk about a knowledge graph versus an OKN and how they interrelate and so on and what's important about them. And then I'll talk about convergence and how KGs and OKNs support convergence and actually kind of a little bit what convergence means in this case. Thirdly, I'll talk about the lessons learned that we've had so far in deploying knowledge graphs at scale, especially when we start talking about billions or multiple billions of triples. And then finally, I'll end with some thoughts about what we can do to really advance the state of knowledge graphs and OKNs as cyber infrastructure. Oh, and so first up. All right, so I guess the story with knowledge graphs really start with data, right? And the data can be in any format that you want, right? Data is data is data. It could be somewhere in the cloud. You could have a data lake. You could just have a collection of CSVs, Excel spreadsheets, pandas tables, or pandas data frames rather, and so on. It's just this heterogeneity of data sources, right? And that's not really always working out so well. It's hard to extract meaning from it if it's in all of these different formats, and it's just hard to integrate. Get the top level overview is just missing. One way to kind of improve this is you start talking about data as a graph. When you're at one particular piece of data, you can move to the next node in the graph, and we would call these relations, right? It's important to note that graph data, or data in a graph, is not necessarily a knowledge graph. I would guess that this is a particularly contentious take on it. People who've put in a lot of work into building a Neo4j um, graph, right, would maybe contend that their output is a knowledge graph, right? But in many ways, when you're just looking at graph data, it's not so different than a relational database. It's just organized. The format of how the data has taken is now in that graph style. So what actually does make the knowledge graph, right? And so I would contend, and many in my research sphere would agree, that it's when you start adding the actual knowledge, right? Data is just a set of facts that are organized by relations, but it's when you start annotating them with class information or constraining how the relationships behave, right? Now we're moving from data to knowledge. We're going up what I like to call the metadata scaffolding. We've got one step up, so now we're not talking just about what the data contains, but what the data is about and how the data relates to each other. And this is how we generally differentiate between knowledge and data. And so knowledge is that scaffolding. It's the thing that gives structure to the graph, to the data graph, and now it's the knowledge graph. It is important to note as well that we do not particularly constrain what a schema means, right? You could have a shackle schema, so you're talking about a closed world assumption, where it might just be a way to validate the data in such a way that particular nodes always relate to other particular nodes in a certain manner. Or it could be something as sophisticated and semantically rich as OWL. They both have their benefits and drawbacks, but this is really where we're starting to look at knowledge graphs. So if that's a knowledge graph, then what is the open knowledge network? So the open knowledge network is really when multiple knowledge graphs have been deployed and they're working together. Uh, there's not going to be a single knowledge graph that rules them all, right? To borrow from Tolkien. If there was, we'd probably have it by now, or Psych would have not failed back in the early aughts. For some definition of failure, of course. It would be a lot more prominent, I suppose. So yes, so what does it mean to kind of work together? So if we don't get one knowledge graph that talks about everything in the world, that means we're going to have individual knowledge graphs for different domains. So maybe one for geospatial science, one for healthcare, one for mathematics, or something more nebulous, right? And then we can kind of fractally nest them as well, because there's so many different aspects to these fields that perhaps we need to be even more granular. So pharmacology and biomedicine would be distinct, but very, very related. So what does it mean to be related, and what does it mean to be cooperative? And this is something that we're still trying to figure out. I'm not sure how many of you are participating in the innovation sprint for the Open Knowledge Network. I think Melissa, I saw there once, but not so sure on the rest of you. But it's a little bit of an open question, and there's two main discussions right now that are occurring within the open knowledge network community, and one is based out of some sort of blockchain remote procedural call architecture that I must confess that I don't understand so well. Um, the competitor, loosely speaking, would be this notion of semantic mappings. So if you have a knowledge network, or sorry, a knowledge graph that's talking about a particular use case that involves, say, geospatial semantics, like essentially it just incorporates space and time in some way in your knowledge graph. And maybe you have another knowledge graph talking about hazards, then maybe they should have a semantic mapping between their different notions of space and time, right? And it's once you have a common base of understanding, you have some sort of mapping from one knowledge network or one knowledge graph into another, such that you can federate a query over them. Now you have a knowledge network. Now your data is working together. Now your knowledge graphs are working together, and now you have an OKN. And this is roughly the take that the innovation sprint is going. They're developing, I don't know, 15 some odd use cases spanning from compounding disasters to healthcare communication and financial stuff, and it's all the open knowledge network needs to be able to support any particular one of these use cases, and by doing so we need a collection of knowledge graphs, each one in these particular domains that work together. And so the semantic mappings will ensure that we have a common basis for communicating between knowledge graphs. So just in summary, we go from data, graph plus a schema, or the knowledge graph, to cooperating KGs, or the OKN, right? And remember that the schema is the important part. It's the thing that gives knowledge structure and a way to communicate between knowledge graphs so that we can have an OKN. All right. So with all that said, what does it, what are some of the goals that we want out of an OKN, and why are they important, and so on? So here, for example, I've mentioned KnowWhereGraph already, but I'll talk about it a bit more in the next section. But KnowWhereGraph deals a lot with places. It's extremely geographically centered. We call them placial queries. And it's essentially a way of clicking on an area or investigating an area and getting all sorts of data back about what's happening there, what is there, what happened there before. Spoke is another knowledge graph that came out of Track A from the Convergence Accelerator at the NSF. And they deal with medicine, genes, diseases, pharmacological data, and pharmaceutical data. And so when we get these two knowledge graphs communicating with each other, and we have a semantic mapping between each of these things, we can actually generate extremely powerful queries that allow us to um, investigate consequences of both place and space and time and chemicals that cause diseases, right? So if KnowWhereGraph contains data about all of the EPA Superfund sites, right, and then Spoke contains all of the data about the particular volatile chemicals that could be found in the soil at those Superfund sites, and then KnowWhereGraph in turn contains information about places that are risk due to climate change, and then maybe another graph that I don't have pictured here called UFOKN, which is about urban flooding, might be able to also tell us where the places that are going to contaminate the water supply. And so all of this together, we get this, this powerful way of querying across domains. Um, and so I guess I kind of spoke a little bit too soon, right? Because UFOKN here could be this orange hash box, which allows us to answer that very particular question. I've added in another node to the diagram here called the authoritative entity disambiguator, which is just a really buzzwordy way of saying Wikipedia or Wikidata or DBpedia. It's some place where the named entities, the important instance data, can be mapped, say, through owl same as, some way of saying this thing and this thing, they're actually the same thing. And if you have multiple graphs that are doing that, when you are looking at one graph and you know that it's the same thing as something that's in Wikidata, you can possibly query all other graphs by saying, hey, look, I want to know everything about Douglas Adams. And if it's in the graph and they've provided the semantic mapping, you should be able to federate that query and go say, give me all of the things about KnowWhereGraph, or sorry, about Douglas Adams that are in KnowWhereGraph, and so on. And so once we have this way to make sure that all of the knowledge graphs are working together, voila, we have an OKN, and we're solving multidisciplinary problems essentially just right off the bat. So yeah. Now, with the first half of the talk done and all of that background information, let's talk about actual things. So the KnowWhereGraph. The KnowWhereGraph is a Track A Convergence Accelerator program. So that means we got $5 million in funding plus some extra in supplements and over the time, and put together a huge team. So we have 12 organizations, possibly more. I might have lost count counting the logos on one of our slides. And we regularly have all hands meetings with some 50 collaborators. And what we did is we took 30 thematic and placial data sets from publicly available data from the United States government, NGOs, and other just open data, and put it all together. So we took upon ourselves essentially this upfront cost of doing the data integration. And then on top of that, we married all of these data sets together with what are called the S2 cell hierarchical grid system. Excuse me. And what this allows us to do is to click on any particular area in the entire world and automatically identify what the geospatial overlap between these other thematic and placial data sets are. And for example, we could click on any particular S2 cell that occurs in California and identify how much or little it has been contaminated by ashfall from the closest smoke plume and therefore wildfire, and whether or not that affects the taste of wine or leafy greens in the area. So it's just a very interesting and very powerful way of investigating what's happening around the states and around the world. The result of this is that we have close to the largest public open source knowledge graph in the world. We're sitting at 12.5 billion triples as of this morning. And it has a really cool schema, as we'll see on the next slide. And that's what kind of makes it the knowledge graph. Whereas you talk about the LOD cloud, or the linked open data cloud, which has some 31 billion triples in it, but it does not have a consistent schema. They're just kind of linked data. So it's open to interpretation whether or not you want to call it knowledge graph, or if it's just more like a amorphous data cloud. Semantics, though, that's why we're here. And then on the other hand, there's the Wikidata RDF interpretation, which sits at 1.1 billion statements, but this is probably off by a factor of 5 to 10. Hard to tell because it's not natively in RDF. So with qualifications, KnowWhereGraph, very large, perhaps largest. So what did we do in order to make all of these data sets work together? And so what you see here is an incredibly tiny version of the schema diagram, so a graphical representation of the logical structure of the knowledge graph, of the KnowWhereGraph. So we used a adaptation of the modular ontology modeling methodology, which takes a big use of patterns to kind of rapidly scale out a knowledge graph schema. This, what you see here, is as of December. So as of a couple weeks ago, we rolled out version 2 of the schema, and it would be impossible to show you anything meaningful on a slide because it's quite large. But it suffices to say that we leveraged the SOSA SSN, so the sensors, observations, sampling, actuators, ontology, the semantics sensors network ontology and the quantities, units, and data types ontology, in order to very quickly get off the ground and say, this is how we're talking about physical observations, this is how we're talking about units, and this is how we're talking about the observed properties of particular data sets. So this is probably the most important and most interesting slide to you guys. What are the lessons learned that we had while pushing the envelope of what's possible with scaling a knowledge graph? In terms of infrastructure, there's some caveats with this. We are at the edge of what's possible. GraphDB is actively struggling to manage multiple versions of 12 billion triples. So we have 3 versions of the graph that have been evolving over the years, the last 3 years. And some of them are subgraphs and some of them are just the older one that tools still depend on. GraphDB, even running on a $25,000 server, simply is not functioning so well. What else? We have the efficient queries. So simply based on the sheer volume of data that we are querying against, even the most efficient queries can be extremely slow. We attempted to mitigate this by managing subgraphs, so like creating named graphs for particular, maybe per data set, but this results in duplicated triples because the identical triples are now now unique because they have a named graph that's inside of them, and then Sparkle updates over named graphs are extremely difficult, at least with GraphDB. And then the other thing is that even the biggest knowledge graph triple store provider right now is probably GraphDB, and arguably it's Amazon Neptune. But Amazon Neptune really runs with labeled property graphs, which are not necessarily triples, even though there's a bridge being developed called RDF star. But critically, they do not support GeoSparkle. Or Lucilla was saying that it's on their roadmap to do that, but that doesn't help us at this moment. But even then, there's no open source scalable architecture for deploying knowledge graphs at scale with GeoSparkle support. Some other lessons that we learned over time is that agile methodologies are extremely difficult to deal with when you're talking about materializing some several billion triples, especially if you have data sets that need to be spatially integrated with each other. That sort of topological analysis is quite computationally expensive, especially if you're dealing with fine-grained geometries. And so a strategy for validating data very early on is extremely necessary. And in retrospect, it's extremely obvious, but that's what they say about hindsight, right? In the same line, solidifying the schema early is extremely valuable. There are places where agile is necessary, software engineering, even knowledge engineering to some extent. Building a knowledge graph, if you are building a large one and you make a fundamental change to your schema, you have to do everything over again. Sometime it would technically be possible to write a Sparkle update that maps triple structures into each other, right? But as I said before, Sparkle updates aren't quite supported at the scale that you would need to for KnowWhereGraph. And so ensuring a sort of not quite waterfall, but something that is you're very upfront about your requirements. You can't rush those, and that the identifying the knowledge or the schema is extremely valuable upfront. All right, so talking quickly about advancing cyber infrastructure, especially when it comes with scaling, is we need to do this sort of scaling the semantics, right? And so I know I just said that agile has its place, and the thing is, we just don't know where that place is. Not so well. Waterfall can be helpful, but it slows things down, and we need to be able to scale quite large, especially if we're dealing with 30 to 50 data sets that each require their own data integration, right? One way that I think we can do this is with the use of patterns. Buying into a pattern-based methodology is also quite valuable. This is kind of my formal training is with pattern-based methods, and every study that I've ever done has shown that it speeds things up so quickly and broadens access to schema development, because you no longer have to be an ontologist to understand. You just plug and play with particular patterns. And so Commodity, which is a piece of software that I wrote, I guess this wouldn't be a presentation if I didn't have some shoehorn in my own self-advertisement, but it's a graphical way of dealing with ontologies. You drag and drop patterns and you connect them via relations, or you change them to suit your needs. And this is how we did the KnowWhereGraph schema is dealing with this, and we modified patterns and we got specific data sets out quite quickly. Many of the other problems were largely with connecting them together and the sorts of pitfalls that occur with people with different conceptualizations how patterns worked. So it was an interesting problem and something that needs to be looked at in the future. All right, so scaling deployment. As I said before, dealing with the sheer volume of data can be quite challenging even for efficient queries. GraphDB, for example, maintains a couple of different tables, ways of indexing the data, so that way you can try and write your queries in such a way that they'll hit the specific indexes first. Unfortunately, there is no transparency in how these indexes are constructed or even which indexes are there. What we're really missing is essentially Apache Genofuseki, for example, which is open source, just needs a lot more attention on it, so that way we can make sure that it's going to scale at the same way that the enterprise software does right now. And this will allow us to sort of examine how the indexes work, and also doesn't break the bank for smaller firms. Of course, the software that can handle graphs at scale, query optimization. And then there's also low-hanging fruit with taking a look at other indexing software. So Elasticsearch, should be a lowercase s, is a way of building extremely fast faceted queries. So essentially looking at all things of a certain type. We've done this ourselves in KnowWhereGraph, and this exponentially sped up many of the simplest queries and most common queries that we needed to execute. And finally, scaling convergence. I think this is the last slide, but is we need to essentially agree that alignment and semantic mappings between knowledge graphs are the way to go about making an OKN and making sure that they're scaling and working together. The 5-star knowledge graphs is something that we're putting together on guidelines for what it actually means to put together a knowledge graph. Yep. And then, of course, the final piece that I should leave you with is make sure that during the construction of a knowledge graph that we're using existing standards. It can be quite difficult to communicate with things that are not using the standards. So, for example, using RDF and OWL or Shackle from the W3C is extremely recommended, because it's just right off the bat you have that baseline interoperability. Oh, scaling interaction, last thing. Okay, so this is dealing with making sure that people are understanding and being able to utilize the knowledge graph in the end. And then, of course, just simply educating them on what a knowledge graph is and how to use it. I won't go into details because I think I'm a little bit over time. So yes, I am happy to take any questions or have any discussion about whatever you would like. And thank you for listening to my talk.
Well, thank you. We have a little bit of time for questions. We want to leave a little time at the end for hub updates, but we're doing okay. If you've got a question, maybe just jump in. We've got a relatively small group.
Hi, I do. I've got questions. Thank you. So, just to let you know, I actually am wrapping up a paper that's going in to a journal called Library Trends. It's a Festschrift for my advisor. And anyway, I've cited and used KnowWhereGraph as an example in the paper. So hopefully I've gotten some things right. But here's my questions. I'm not on the technical end of things. I'm on the use and users end of things and the data curation. So combination of those areas. And I'm working right now on sort of AI readiness kinds of things. So, but my immediate question is about the data, and that is that I expect that we will have a tremendous amount of data, the underlying data resource management that's going to have to happen. It seems to me we're going to need all kinds of data engineers and curators, if you will, making sure that in the building out of graphs, in the federation of graphs, that the underlying data is what we think it is, and the quality is what it needs to be, and things like that. Anyway, just would like to hear your thoughts on and experiences with, running into bad data as you've been building, as KnowWhereGraph has been built out, and bringing in all these data resources especially from the federal government, right? What has been sort of your experience with quality issues and management of these data resources, and are there implications, or is it completely irrelevant? I mean, so that's my question. Thank you.
Yeah, no problem. Thanks for the questions. Hope the paper goes well.
Thank you.
So when it comes to data quality from the US government, in general, it has been excellent, which may or may not be a surprise depending on how you view certain functionings. There's many things that work well simply because they are bound by law to do it a specific way, and therefore it's predictable. So anything that comes out of USGS has always the same mapped projection. It is always described using some ISO standard. I can't remember, like 1906, 1926, can't quite recall, but it always describes exactly what's in every single one of those data sets. There are, however, other places that we have run into problems, and that is generally with NOAA data. And this has to deal a lot with place. The ways that places are referred to is not necessarily consistent across agencies. So trying to do that sort of disambiguation has been a little bit of a trial. One of the other things that we ran into are that the agencies don't talk to each other about certain things, which that I think comes as absolutely no surprise. The big piece that we can speak to is when we're talking about a fire. There's the National Fire Center. There's FEMA, and there's NOAA, and they all track wildfires for different reasons. And they all call them different things. And we have a whole bunch of data about the same fire, and we don't even know it. It's quite frustrating. And then sometimes when you're looking at what is it, the NIFC prescribes a point data for a particular wildfire, whereas the National Tree and NTBS, I think is what it is. They give us an extremely detailed day-by-day analysis of the entire polygon that the burn scar, that's what it's called. And so when you're trying to query across all fires, you might get some duplicates, but they have different geometries, which is annoying, and other things. So these sorts of problems are the ones that we ran into. Not so much that the data is bad, is that there's this extra disambiguation step that we ran into. Other ways that we ran into quality assurance problems were from NGOs that were putting out data that were not in an expected format. So for example, we use the Global Administrative Regions database, which kind of threw out the international standard for country codes right out the window. They don't talk about countries. They don't use the names for countries that they're supposed to. And so when we're looking at a global database from the United Nations, for example, that does, we have to do string matching to determine that the Vatican City is actually supposed to be called the Holy See, right? Or we have these little annoying manual rules that we needed to do. It's actually with the enslaved ontology. That is where this sort of long tail quality assurance comes in, because that is dealing with a bunch of historians who are quite good at their jobs, but they are not by any stretch data engineers, right? So their data generally exists as Excel spreadsheets, and that's what they put out. And so trying to do the quality assurance across multiple Excel spreadsheets when they're calling the same thing different things across 12 different historians, that's where it ran into. I would take a look at their publications. That's from Michigan State, the Matrix, led by Dean Rayberger, who would be able to give you some of their experiences on that. He's an excellent guy. He works with KnowWhereGraph stuff. But that's probably where you would get more of that long tail quality assurance.
Cool. Thank you very much.
Yeah, no problem.
Anyone else want to jump in? If not, I will. I might ask kind of the counterpart to Melissa's question. There's a lot embedded in the graphs, and I'm sorry, in the knowledge graphs. And how do you keep them from, and also we live in a world where there are many truths. How do you keep those from getting to be a little bit too brittle, especially when they're as large as the ones that you're talking about?
That is a really good open question. So when it comes down to KnowWhereGraph, there was very little of this problem. So it's still a little bit open. When it came down to scaling out the enslaved ontology, because you have multiple historians talking about the same historical event, and they do not agree with each other almost as a rule. What we generally do is we call it a record based. So every node is essentially X datum according to somebody, to some authority. And when we would create the tinier knowledge graphs for each one of the individual historians' data, because it is because it is described in this way, it's just simply a collection of records, right? And then you could say, give me all records about X topic, and then all of a sudden you have conflicting answers, but it's fine because the conflicts are not about the truthiness of something. You got records of their idea of the truthiness. When we're talking about doing this at scale, provenance at the instance level explodes quite a lot. However, what we've investigated, at least with knowledge graphs that use SOSA SSN, which is it is a W3C recommended way of dealing with sensor observation data. is that we encode the provenance via the observed property. So what we say is it could be an observation about some particular area of space, but the observed property comes from a data set, right? And so you could have multiple observations looking at the same space and possibly measuring the same thing. So for example, the air quality index, right? It's a terrible example because only NOAA does that. But if we had two things like a citizen scientist saying it, the observed property would be you have the observed property of nitrate content according to NOAA, and then you have the nitrate content according to Joe Smith, the citizen scientist who's running their own little tower in their backyard. And off the top of my head, I think that's probably one of the ways to go forward.
Oh, there's so much to ask, and but
I
I might
happy
leave it there.
Okay, I am happy to receive any emails. So if you have more questions, feel free. And if I can't answer them, the good thing is I can just forward them to the rest of the KnowWhereGraph team and you can get your answers that way.